In this video, we are going to look into some of the questions and answers of special relativity. This video is meant for students and science enthusiasts. However, I would like to emphasize that we are going to learn, analyze, critically evaluate what are the questions that come in an examination which is related to special relativity. I've made certain problems and solutions which pertains to length contraction, time dilation, muon decay and twin paradox. I would be continuing with this question answer series of videos not only on special relativity but also in nuclear physics, quantum mechanics and real analysis. This is the first video in which I am trying to analyze and answer some of the questions which would help the students to get a better idea on special relativity. My name is Shaunak and we are watching this video on my channel Physics for Students. I welcome you to my channel. So before we go ahead and directly deal with the question answers of special relativity, I just want to tell you what is the objective behind this video. I'm making this video in order to give an idea on the questions of special relativity, also to identify the common mistakes which students make and to rectify them. It will help you to make the underlying concepts very clear, and finally we need to understand the questions deeply and find the solution, because some of the questions do have the answers hidden within them. And finally, these will help you to brush up the concepts of special relativity. So without further introduction, because it has not much to say, we will go directly into the problems. So the first question that comes is that if an object approaches the speed of light, its mass becomes, and you are given four options. One is 0, second it remains the same, third it doubles, and fourth it becomes infinite. Now hold on, I know that this is a pretty easy answer to this object of this question, that what would be the mass if it object approaches the speed of light. But I would like to give you a very thoughtful understanding in some of the common misconception which happens. So this is the question and we are going to take forward with this. Now whenever we are dealing with mass, especially in special theory of relativity, we know that we need to deal with relativistic mass. Now when we talk of this equation, this represents the mass of the body, v square is the velocity and c is the speed of light. Now as the body approaches the speed of light, that means the body is running so fast that it approaches the speed of light, the velocity becomes equal to c. Now when velocity becomes equals to c, in that case we can substitute this value and the denominator v square becomes c square and the c square gets cancelled out, and then m equals to m0 root over 1 minus 1, which leads to 0, and when anything is on the top and at the denominator it is 0, then there is a confusion whether it is infinite or undefined. I find this confusion in many readings and further studies, that some people say that mass is infinite, some people say some mass is undefined. So let us try to find out what actually it is. So I would say the mass becomes infinite. Why it is so? So if we try to identify, say for example we get one apple and we divide that apple into 10 units, then we divide that 10 units divided by 5, we get 2. We divide it by 2, we get 5. That means the denominator, if we are decreasing in number, the numerator increases. So 1 by 1 equals to 0, 1 by 0.1 equals to 10, 1 upon 0.01 equals to 100, and so on. So you can see as the denominator decreases, the numerator increases, and 1 upon 0 could be plus infinity. On the other hand, we divide it by minus 0.1, we get minus 10, and then we get minus 100 and so on, and then we get something which is minus infinity. So one side we are getting on a logic that it is plus infinity, on the other we are getting minus infinity. So you see that while the denominator in both the cases tends to get nearer and nearer 0, as they get closer the result keeps on going, increasing and further away, and eventually they are extremely different. So positive and negative infinity, they literally theoretically go from one end to the other. Just like this number line, the negative infinity goes in this way, the positive infinity goes in this way. So we are really unable to understand and define what it is. So they literally go from one end to the number line on the negative and the positive. So which one is it? And hence we tell that it has been decided to be written as being undefined. So the thing is that you can call it undefined. I would prefer to call it infinity. The basic reason is that if the number line stretches from negative to positive infinity, we really don't have any answer, and hence we call it undefined. So this is a very critical and an important concept between undefined and infinity. However, this would be, the mass would become infinity. So coming back to the question, here you are given 4 options. So the answer is infinity, right? The mass will become infinite, and this is the right answer, and it is a green tick. Okay, so next we go to question number 2, and we see length contraction happens only when the body is perpendicular to the direction of motion, it is along the direction of motion, it is parallel to the direction of motion, or it is both A and B. We need to find it out. So this is the question, given 4 options. Okay. First of all, the reason length contraction occurs in the first place is to preserve a constant speed of light of all inertial frames. So if an observer, say this person, is moving on the x direction, then the length contraction happens in x direction. Why? Because you have no motion in the, so to preserve the speed of light, because you don't have any motion in the y direction or in the z direction, so no length contraction is needed in the perpendicular directions. So we can say that a body with infinite dimension will always contract in the direction of motion, and the length of contraction is given by this formula. So a square sheet will contract in either direction by a factor of this. A sheet moving in both directions will experience contraction in both dimensions. So length contraction is motivated, as you say, by a need to keep the speed of the light to be same. Here is one of the picture. This is using Lorentz contraction. So you can see the moving objects are shorter. So when v equals to 0, this becomes shorter. V equals to 0.3, this becomes shorter. Then you see that the contraction happens. So moving objects are shorter in the direction of motion. As with the relativistic effect, this mostly shows up close to the speed of light, and then it becomes this. So when you see that v equals to 0.9 c, then the shape of the sphere, it is contracting and it is elongating, right? So the measured length of an object along the line of relative motion is contracted while measured lengths perpendicular to the motion are not. So this is another illustration which shows that the circle, as the velocity increases, it contracts and it becomes a little bit longer. So the length particulars are not, because in order to preserve the line of motion or the speed of light, this is being done. So coming back to the question, length contraction happens along the direction of motion. So this is the right answer. We will see a few more examples which will elaborate and make you understand about that contraction happens along the direction of motion, not in perpendicular, parallel, or both A and B. Okay. So here is a small question. Another. The question says that the speed of a fast moving electron with total energy 2 mega electron volt is nearly what? 0.96 c, 0.99 c, then 0.98 c, and 0.97. So just note that we are given the total energy to be mega electron volt. Okay, so this is the question. So the relativistic particle is something which moves with relativistic speed, and the speed is comparable to the speed of light. We know that the total energy will be equal to rest energy plus kinetic energy, and this is the equation which gives that. And we know that the mass of an electron m equals to this, and the speed of light is this, and 1 electron volt equals to this amount of joules. Now we need to do a little bit of conversion here, because from mega electron volt we need to convert it to joules, because that is the fundamental unit. So given the conversion, 1 MeV equals to 1,000,000 electron volt. Now 1 joule equals to this, and from here what we do is that we calculate the value of 1 joule equal to 1 volt into times this much amount of electron. So 1.6 times 10 to the 1 minus joule equals to 1 electron volt. That means however many electron volts we have to calculate, we just need to multiply it by this. So 2, 3, whatever. So this is just a quick derivation which shows that from MeV we can go into joules. Now the question tells that the question is that 2 MeV. So we will multiply, first convert the 2 MeV, then multiply this by this, and what we get is 3.2 into 10 to the power minus 13 joules. So we take it forward and we use this Lorentz transformation, and where we know that the mass of the electron is this. So we get 3.24, which is the go to the previous part, we got this one, right? The joules part. So we plug in this value, and you just have to do a little bit of calculation on this, and it gives the value of 3.9078, and the velocity v becomes 0.97. So here the basic thing is that it is not much of a big calculation, just you have to plug in the values. But most importantly, what you need to do is that you have to convert that mega electron volt to joules. Now let us go back to the question. Okay, there's one point I would like to make an attention, that if we considered kinetic energy as half, that is half mv squared, that is 0.5 mv squared. So what happens is that it would result into this, and if you plug in the values over here, it would become this, and this is impossible. That is, it exceeds the speed of light, which violates the special theory of relativity's tenets. So I'm not saying that if you're given a problem, it would not come to something more than the speed of light, but you know, based on the principle, it generally doesn't happen, right? So it violates the speed of light if we consider kinetic energy to be this. Coming back to this, what is the answer? It is option D, that is 0.97 C, which we have found out, and that is how. So the basic takeaway of this is that if we take the kinetic energy to be 0.5, then it exceeds the speed of light, which violates one of the postulates of special relativity. And if we take 2 mega electron volt, we need to transfer and convert the unit to joules. Okay, here is a very interesting question. An astronaut at rest has a heartbeat of 65 beats per minute. Remember that the usual average heartbeat of a human being is 60 to 100. When the astronaut spaceship is moving at 0.6 C, what is the heartbeat as measured from the Earth? So clearly what it tells is that the heartbeat is given, the movement of the spaceship is given, and astronaut ship is given, and we need to find out the heartbeat. So given are these three options, and we need to find it which one. So let us now see how we can solve this problem. So there are three important concepts of special relativity. Just a quick recap. One is this one, which is called length contraction. Another is time dilation, and the third is called relativistic mass. So all of them are being given by Lorentz transformation. Contraction happens, time dilation, relativistic mass. Now when the spaceship moves, right, we are given F equals to 65. That means we can take T equals to 1 upon 65. V is already given as 0.6 C. We use the time dilation factor because we need to find out the time, that is a heartbeat. So 1 by 65 is this. So what we get, T prime equals to 1 by 52. That means 52 beats per minute, right? So this is very simple. If we are given 65, so we take up the time, and then we take the velocity of the spaceship, and then we put it into the Lorentz transformation, and we get 52 bits per minute. So what is the answer? The answer is 52 bits per minute, and this is how it is beating. So I just thought to give you a slight kind of an animation. So this is another MCQ which deals with length contraction. Okay, this is something important. A suitcase measures 50 cm times 25 times 10. A traveler takes the suitcase on a train which is moving at a velocity 0.6 c. If the suitcase is placed with its length along the train's velocity, find the dimensions measured by the ground observer. Most important in here is that we are given those four options, right? Which one would be that? And here what we need to do, I have underlined, is that remember that it is length is along the train's velocity. I will like to show you a quick kind of a illustration which makes things clear. So suppose this is a traveler's suitcase, and this way it won't happen. The breadth also won't happen, only because it is moving along the train's line, so the length would vary, that is 50 cm. Here is the train, and these two factors won't vary, 10 and 25 won't vary, and what it vary would be this one, which is perpendicular to this. So the part parallel to V will only contract. Simple, we take the length contraction, we plug in those values and we get 40 cm, which is basically the amount of contraction. Now we go back to this question and we get 40, 25 and 10. So we already got 40, so 25 cm automatically comes, and this is considered to be the right answer. Right, so again, as I told you, the important takeaway of this question is that how we can measure the length contraction, it should be along the train. So that is why the length only varies, the other variables remains constant. Okay, now we come to a little bit descriptive of the descriptive questions. So the first one tells that the Earth and Sun are 8 light minutes apart. There are two events A and B occurring at t equals to 0 on Earth and at 2 minutes on the Sun respectively. We need to find the time difference moving at u equal to 0.8 c, and we have to repeat that taking the opposite direction. That means plus and minus at u is equal to 0.8 c. How do we approach this problem? So I have written certain scripts. I mean to say you can use different. So I have mentioned delta t to be observer. This one Earth to Sun, this is Earth to Sun delta t, and u upon c square. This is quite simple. I've just taken this formula, gamma equals to 1 upon 1 by u square by c square, instead of I have repeatedly used u instead of v because in the problem it is mentioned u. So putting the values, we get 2 minutes minus this, which actually comes to minus 7.7 minute. Now this is something very important. This means that it has been occurring in the past. That means it has happened earlier, which leads to the conclusion that event B happens before event A, right? So minus some time means if you take the Minkowski diagram, you will see that it is the past, right? Now we have to reverse that, right? So minus, we take it as plus. So when we do the reversing, we get the value equals to 14 minute. So this is the total problem which we were given. So we get A equals to 7.7 minute and B equals to 14 minute. Oh, I'm so sorry. Yeah. So this is basically the time difference which comes is minus 7.7 minute, which means it has occurred to past. And you see I have written here that this is the past and repeated observer is in this, so that comes to 14 minutes. So the key takeaway of this program is that if anything which is the time which is coming in the negative direction, then it has happened earlier, right? And most importantly, during the Lorentz transformation, use those values or the variables which are given in the problem. It will be easier for you to solve. Okay, now a muon has a lifetime of this, and it is created 100 km above the Earth and moves towards it at a speed of this. Now I would like to give you a brief idea about what is a muon. So problem is that at what altitude does it decay, and according to the muon, how far does it travel? Now muon actually, which is represented by this Greek letter mu, is an elementary particle which is something similar to the electron with an electric charge of -1 electron, and it is classified as lepton. This is the muon is not known to have any substructure, that is it is not thought to be composed of any particles. The muon is unstable on a subatomic particle, which means it has a mean lifetime of 2.22 mu seconds, mus, which is much longer than many other subatomic particles. As with the decay of the non-elementary neutron with a lifetime around 15 minutes, muon decay is slow because the decay is mediated only by weak interactions rather than by strong or electromagnetic interaction, and because the mass difference between the muon and the set of its decay products is small, providing few kinetic energies of freedom for decay. So muon decay almost always produce at least 3 particles, most includes an electron of the same charge as the muon and 2 types of neutrinos. So this is just a kind of a quick overview of what is a muon. So this is 2.2 microseconds. Okay, and so this is the value of the muon 2.2 multiplied by this. And then we come to the explanation. What we do here is that we take the time dilation factor, and then we know the muon's lifetime is tau. The distance the muon travels is distance equal to velocity into time. Velocity multiplied by time multiplied by the gamma factor, because time won't be the same time. We have to take the Lorentz time transformation. So here is a little bit a longer calculation. I've just plugged in the values. So this is the muon's velocity, this is the muon's lifetime, and this is the speed of light. And according to muon, if you do the calculation, it has just traveled 590 m. So this is a nice example of muon decay. You will see in special relativity, it comes with a lot of this kind of problems. So the question or to the answer is 590 m. Okay, this is a very interesting question. I would like to tell you these are from the Yale University, the famous Yale University questions. So an observer S, it lives on the x-axis, right? It flashes a red light, which is around 1 to 10 meters. Then at 4.96 milliseconds, he sees a flashlight at 480 meter. We need to use the subscripts R and B to label coordinates of the events. So question is that what is the velocity relative to S of an observer S prime who records the event occurring at the same place, and which event occurs first according to S prime, and what is the measured time interval between these flashes? Okay, so most important thing is in red, that 4.96 milliseconds. There is a kind of a conversion which we will just come across. So millisecond, this one is called microsecond. It is a unit of time. 1 millionth of a second is this. And you can imagine the example of 1 microsecond is strobe light, or a protein folds itself in just, it is so minuscule, so small, it's very hard to imagine. Now 1 millisecond equal to this, so 1 millisecond would be 10 to the power minus 6 second. As per the problem I drew, I have drawn two axes, x and y, but it is mentioned that the person is living in x-axis. This is the red light flash, and it happens at 1 to 10 meter. Now you see what I have done is that although it should be in the x-axis, just for the in order to become better to view those for the students, especially to you who are watching this video, I've just drawn it as at an angle, but it should be along the x-axis. Then he sees the blue light flash at x is equals to 480 meter. Now physically you should note that what happens is that the observer sees the flash of red and then travels at a velocity v, this one, the time t, and it travels at a velocity v such that he arrives just in time to see the flash of blue. So he travels at a velocity v just that he arrives just in time to see the flash of blue. So what we can do now, we can go ahead and solve the problem. If you want to take a snapshot of this, you can. I mean to say, there is no harm. You can draw it as per your own convenience, but I have just drawn it in order to show you. Okay, so we find out that x sub r minus vt velocity time r equals to this. So these two r's are basically with the frame of reference of x, and because we are told we have to do r and v, so this is vt r and this is v. So what we do is that we simply plug in the values and we take at the denominator the time, because we have to deduct the time factor also. This one is 1 microsecond. Now you see, that is why I have been showing you, let us go back, this one. This is required because that microsecond is the catch of this problem. Without that it is simple. The problem is very simple. Only that we need to follow the microsecond part, right? Then we get this value. Again we are getting a minus sign. So what that implies is that velocity relative to s of an observer s prime, that means if it is minus, the observer in s prime frame of reference sees event r happens before event b. Obviously, as I have been telling, that this is the catch, this is the key takeaway, that s prime frame of reference sees event r happens before b. Okay, now we use the invariant space-time interval. Why? I will just show you. This is the space-time interval. We plug in those values, and again this, which leads to 4.32 milliseconds. So we have to basically deal with two of the problems. The first one, which is already calculated, now we are approaching the second part using the invariant space-time interval. Now putting the values, we get this, which is a little bit longer one, which is t prime r equals to the gamma factor of TR minus VC squared. This is when the Lorentz factor, if you remember, and multiplied by this gives to 2.27 mu seconds. Again T prime B, because it is the B frame of reference, multiplied by this gives to 6.59 mu seconds. So ultimately what do we, here also we see that event R occurs before event B, because the value of R is 2.27. That means it happens earlier, but the value of B is 6.59. So you see the catch of this problem is that first it was negative, so that is why it happens earlier. Here it is positive, but comparing two values we get R occurring before event B. Okay, so let us recap. We did a lot of calculations. So first what we found is that what is the velocity relative to S of an observer S prime. We did this calculation, and what we found is this. The observer in the frame reference sees the value. We got the velocity as minus 1.47 times 10 to the power 8 m per s, and it happens before. And what the second question is, which event occurs first according to S prime? What is the measured time interval? Then we use for the measured time interval the space time interval. Then we multiplied this value and we got 2.27, and this one is 6.59, which eventually implies that event R occurs before event B. So this is a kind of a quick practice and a kind of a very interesting exercise which I just thought to tell you. Okay, so how do we find the time interval? The time interval is 4.32 mu seconds. 6.59 minus 2.27 gives this value. So I just thought to make it on a fresh slide. Okay, now we come to what is called the twin paradox. Very interesting and very fascinating outcome of special relativity. So two twins, both are aged 30 years, right? They go off into a rocket which moves at 0.8 c, and they experience what is to be 12 years. How old is the twin that remained on Earth when the other twin traveling around space returned back home? I'll just show you a kind of a visual demonstration. So this is the twin on the left hand side, waving tata and bye bye to the other twin, which is who is ready to travel in space. Both of them are age 30, and we need to find this person's age, this twin who is staying at on Earth, compared to that person who will be traveling across space. So it is very simple. We use the time dilation factor, and as per the problem, velocity is this one, time is 12. So just simply we have to plug in those values, and here it goes, and here it goes, and we get t prime equals to 20. Now remember that when the twins started, both were aged 30 years. That means I have to add 30 with 20 in order to get 50 years, right? This is the t prime age. Remember that this t prime age is the time dilated age. But when they started at 30, that means I have to add the age at which that person remained, right? So now we come to the final conclusion. This person, when comes back with a stick on his hand, has grown older, and he's 50 years old, while that other person who has left around 30 years. Okay, this is another simple example. A man who weighs 60 kilogram on Earth weighs 61 kilogram on a rocket, as measured by an observer on Earth. What is the speed of the rocket? So a man who is weighing on Earth is 60, and on rocket it is 61 gram. So now we have to use what is called the relativistic mass, obviously, because we are given the mass 60, 61. We are given the mass and we have to find the speed of the rocket. So we are given this relativistic mass equation. Now remember here, this m is given, m0 is given, c square is given, and b square we need to find it out. This is how we should plot a problem, given the values and what we need to find out. Now here is a small catch, that m equals to 61 kilogram and m0 equal to 60 kilogram. Which one should be the rest mass, right? So this one should be the rest mass, because the person who weighs on Earth has not started accelerating. So we put in these values. 61 equals to this 1 minus v square, and just by calculating we get the value. So the speed of the rocket is this, right? We got the speed of the rocket, right? So what have we learned? We have learned time dilation, we have learned length contraction, we have seen a little bit of mass energy equivalence and the muon decay factor. So do let me know your comments on the comment section, how you have liked the first video and I have plans to get into more detailed and difficult problems on special relativity, nuclear physics, real analysis, and other areas of physics. I hope it will help the students not only to solve the problems immediately, but also have a grasp and complete understanding what is going wrong, what are the common errors, and what backup and precautions should be taken. Please do like and subscribe to my channel and click on the bell icon to get all the notification from Physics for Students. This is Shaunak signing off and promising to come back with yet another question answers on some of the problems of physics. And by that time, I think you will be commenting and sending your views about this video. I wish you all the best for the coming future and promising you to come back with certain interesting videos. Till then, goodbye and have a nice weekend ahead. Bye.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.